So, welcome back, everyone. We will continue from where we left off in the first part. In this part, we will talk about some other techniques that can provide physical layer security by utilizing artificial noise or the addition of an auxiliary signal that can help us improve our transmission. So, this technique over here exploits the one feature in the OFDM, which is the fact that in OFDM, we have some extra degree of freedom, which is the addition of the CB that we usually remove at the receiver after we receive our data, CB. CB is a cyclic prefix, which is a guard period that we append and add to each and every signal or packet that we send over the air, each and every symbol basically. Uh, and this can usually gets removed after it reaches the receiver because the goal of using it is to prevent inter-symbol interference. As soon as we receive it and we prevented inter-symbol interference, there will be no need for it, and therefore we just discard it, remove it, throw it away. So this idea of having this single idea of having something at the transmitter and removing it at the receiver after we are done with it can allow us to improve our security. How? By adding a signal, by designing a signal in an intelligent way that when we add it, it gets added to the whole signal, and therefore anybody in between the transmitter and receiver will see it as interference. The symbol is getting interference from another signal called suppressing signal. But because the signal we add is function of the legitimate channel H between the transmitter and receiver, Alice and Bob, it can only be removed at Bob successfully. Why? Because the signal, when it reaches the receiver, it gets accumulated. It means it shrinks itself, accumulates itself only over the part of CB. So it removes itself from the data and only becomes available because the content of this interference signal becomes only over the CB. So this allows us to get rid of this interference signal as soon when we get rid of the CB. Clear? So this can be used, basically, it was in 2008, something around that date, it was first proposed to improve the OFDM performance by using this type of technique to remove out-of-band emission, to suppress out-of-band emission, out-of-band interference reduction. And then later on, the researchers used it to provide security. And they named it static cyclic prefix alignment for OFDM-based waveform. So researchers from University of South Florida, they utilized it for the first time to improve what? Security, as well as improve out-of-band emission and peak to average power ratio. And the way they do it is just similar to the previous way, and the same math, almost same everything, but the application now is different. So instead of using for out-of-band emission alone, they are now using it for security purposes. And the same researchers extended this technique to another or more powerful technique that can not just exploit the CB, but they said in OFDM sometimes we have some subcarriers that face deep fades, like this region over here, deep fades. So they said, I'm gonna just highlight the deep fades for you here. So here we have deep fades, this region, deep fades, this region is deep fades, and we usually when we send our signal, some of our OFDM subcarriers will face this region, this region, this region, this region. If we transmit our data over these deep fed regions, which means their amplitude is suppressed, in this case, what will happen? We will not be able to decode our data successfully. Okay. However, if we don't transmit over them, then we will improve our bit error rate performance and avoid sending over them. The researchers from the University of South Florida came and said, if it's better not to send anything over here, because the channel here is in a deep fed period with respect to Alice, with respect to Bob, between Alice and Bob. So what if we add artificial noise in these subcarriers that corresponding to these deep fades, so that the receiver, we know that he knows this deep fade, so when he receives them, he cancels them, drops them, throw them away. But for Eve, he doesn't know because his channel is different. And even if he knows, his channel might be good and he might still want to receive over that. But the most important thing, if Eve shouldn't know the subcarriers over which we are sending artificial noise. If Eve knows which subcarrier we are sending artificial noise, he can also cancel them. But since we are extracting this information from the channel between Alice and Bob, which is reciprocal and only available to them, in this case, Eve will not be able to decode the signal successfully. Good. So this is for the signal over here. Okay, now here is also another technique that got published in 2018, 2019. And this technique basically says, can we add a signal on top of our data symbols, in such a way that this signal, when it reaches the receiver, it cancels the interference caused by not using CB. Now remember with me, I told you in OFDM systems, we use CB, which is cyclic prefix, as a guard period, in order to protect our transmission from intersymbol interference. So the authors here came up with the idea that, what if we don't use CB? In this case, what will happen? There will be interference between the symbols. You see this interference over here? The red. So there will be interference. Now, how about we design the signal at the transmitter in such a way that it cancels the interference between the symbols that carry our data? Is that possible? Using some mathematical frameworks and some design tools and intelligent way of processing the data and the signals, researchers showed in their paper that it's possible to design the signal in such a way that you cancel the interference caused by not using CB between the symbols. And the way you do it in a regular OFDM, for example, in the upper side here, you have transmitted data serial to parallel IFFT, you add cyclic prefix, and then you, from the transmitter, you send to the receiver. At the receiver, you take the signal and you pass it through serial to parallel, and then you discard the cyclic prefix, you get rid of it, and then you pass it through FFT, and then equalizer, parallel to serial, and then you receive your data. Now, the proposed system, which is called CP-less OFDM, which is different from regular OFDM in this gray blocks. We don't have, in this new system, we don't have the addition of cyclic prefix at the transmitter, and we don't have the removal of cyclic prefix at the receiver. Instead, we have alignment signal that we add in time domain after the IFFT. And this alignment signal is designed mathematically in an intelligent manner that it can cancel the interference caused by not using cyclic prefix. Now, here is the trick. Now, this alignment signal is function of the channel between the transmitter and receiver, which is Alice and Bob, and both are legitimate and they want to talk to each other. Therefore, the signal, which is called alignment signal, can act as a way to protect our data from eavesdropping, because the signal is designed as a function of the channel, legitimate channel between the transmitter and receiver. And if it can cancel the interference for Alice, it will not cancel the interference at Bob, because Bob's channel is completely different from Eve in a rich scattering environment, and Eve is assumed to be located in a different location than Alice, which is practical and realistic in real life scenarios. So you can see the packets, how we transmit them here, the packets, and we add interface alignment signal on top of them. And after they pass through the channel edge, this interference signal gets accumulated over this part and it cancels this. It accumulates over this and cancels the interference. But for Eve, it will not do the same. It will not do the same because what? Because the signal is not designed as function of Eve's channel, but as function of Bob's channel. So this is regarding this technique. What about this technique? So there are cases where we have multi-axis system. We have more than one user who are trying to communicate with uh, base stations, and we have eavesdroppers. So the problem here is that you have multiple legitimate users and you have an external eavesdropper. Now, for the multiple legitimate user, they are legitimate, but you don't want any user to get the data of the other user. You don't want any user to get the data of another user in the network, even if it's legitimate, as well as you don't want any external eavesdropper to get the data being transmitted between the transmitter and receiver. Okay, so what can we do in this case? So we design a precoder. This is the first base station, let's say. So this is the first base station, sending two data vectors, user one data, user two data, modulate them, then serial to parallel, serial to parallel. We have a precoder A1, precoder B2. These precoders are intentionally added to the system before I50 so that we can design them in such a way that they protect our transmission from eavesdropping, external eavesdropping and internal eavesdropping. And these two branches of the signal will cause interference to each other, but because of the design we use for the precoders A1 and B1, we can cancel this interference. So the user one signal is added on top of user two signal and then sent to both users. And from this base station, we have user one signal on top of user two signal. But as you can see, we use different precoders, a precoder A2, precoder B2. And then both receivers, OFDM receiver user one and OFDM receiver user two, receives these signals. And due to the special design of the precoders, the interference will be cancelled and each user will get his own data. The OFDM user one will get his user one data only, and OFDM receiver user two will get his data only user two signal. So this idea is useful when you have multiple users in the system and you want to protect your data from other users as well as the external users. Okay. how does this happen mathematically? So we have the data x1 of user 1 and x2 of user 2. From the first base station, we have two branches. The first branch, uh, this upper branch over here, we have the upper branch over here and the lower branch over here from one antenna. So this will have a1 multiplied by x1, and this will have b2 multiplied by x2. So so a1 multiplied by x1, b1 multiplied by x2, and from the other base station we have x1 and x2 as well, but multiplied with different decoders, a2 and b2. So then they pass through channels, different channels. The signal received at user 1 and user 2 are given as follows. For user 1, you have h11 multiplied by xt1 plus h12 multiplied by xt2, because the receiver will receive the signal from both base stations. And then after that, you just substitute the value of x21, x22 inside these equations. What's the value of x21 here? x21 is a1 x1 plus b1 multiplied by x2. You just substitute it here and put the channels as they are. Then do some simplification. Sort x1 in one term, x2 in another term. You will get here net term for user 1. Wherever we see x1, we try to put them together. Wherever we see x2, we try to put them together in another side. So as you can see here, we have this term, yes, this term for x1 and this term for x2. Now I'm talking about the received signal at user 1. Now the received signal at user 1, I'm interested in only as a user 1. I'm interested only in receiving what? In receiving x1 data as user 1, because this is my data. x2 is not my data. But if this x2 keeps, if it remains, if it stays, it will cause interference to me, and I will not be able to decode my own signal x1. And the same thing for user 2 signal. User 2 signal, I'm interested in receiving x2, my data, but unfortunately, I'm receiving also another term, which is x1. x1 with the channel matrices and the precoder matrices. And this is interference. This is the interfering term on user 2. So if I want my objective here, my design objective is to get rid of this term and get rid of this term, so that each user 1 can get his own data x1 and user 2 can get his own data x2. In this case, user 1 will not get interference from x2, user 2 will not get interference from x1. So how to design the precoders then? How to design the precoders? So here we design them. We take this term, and we equate it to 0. And the other term, we equate it to 0. The terms that we want to cancel them, okay? And the term, and some terms, the fading term, we equate them to unity. And by calculating these two equations mathematically using linear algebra, we can get the values of P1, P2, the precoding values, that can really achieve this condition. And the same for the other equations. One we equate it with 0, one we equate it with unity, and after that we find out the values of A1 and A2 that are functions of the channel. And if we use them in this way, we will make sure that we will not have interference, we will not have fading, and we will have security against external eavesdropping and security against internal eavesdropping. Internal means legitimate users are listening to each other. External an external eavesdropper, somebody who's not in the network, not authenticated to the network, not part of the network. The network is not aware of its existence. In this case, security can be provided against uh, both attacks, internal eavesdropping, external eavesdropping, and so on. So again, to explain these equations a bit more, what we did here, if you see here, this H11, B11, this is where it's this. This equation is this. I told you this is interference term. I want to get rid of it. Okay. And what? And this is what? This is the factor of x1. This is the term, the fading term. The ideal way of dealing is to get rid of it. I mean, to get rid of it means I want it to be unity. If unity, when I get unity matrix, which means one almost, like one in numeric values, but in linear algebra, in matrices, when we are dealing with matrices, we don't have one, we have unity matrix. But when you multiply the unity matrix with x1, you will have x1 as a result. Therefore, this term over here is coming from the fading part over here. The same when you do calculate mathematically, if you are good in math and linear algebra, you should be able to calculate this. You can take this as an optional homework at home. Try to calculate the value. If somebody gives you two equations like this, assume this is a linear algebra course you are taking, and somebody gave you these two equations and asked you to solve them. What would you do? You solve them by substitution. You say from the first equation, I can see that h11 b1 equal minus h11 h12 b2. In this case, I can put b1 in one side and all the other terms in the other side. And then I come to the second equation and I see b1 here. So I substitute the value of b1 that I found from the first equation in the second equation. And therefore, I will be able to calculate and find the value of B2. Then I use B2 as backward substitution in the first equation to find what B1 is. And therefore, I will be able to find these values. Okay. The same thing goes for equation 2. I have this term that I want it to be unity, which is this term. And I have this term, which I want it to be 0 because it's interference. And then the output is going to be something like that. Okay. This is it. This is an example of how we design the precoders in such a way that they remove interference, remove fading, and guarantee security against both internal and external eavesdropping. Any questions? If there are no questions, we can stop the recording here.